That's why we better get started now. Okay. FTIR spectroscopy. Fourier transform infrared spectroscopy. Here's some, oh, I already answered the first question. I guess that was my turn, right? FTIR, Andy? Fourier transform infrared spectroscopy. What is IR energy, Andy? In layman's terms, it's more commonly called infrared, yeah, but yeah, what do we usually call it? Yeah, they have the infrared goggles, and that just sells better than blank goggles. Starts with an H. Heat. Ah, this thing's not writing. Heat. So Brandy, why is there a break in the scale? A break in the scale? What are they talking about? I think they're saying, see, here's 1,000. Here's 1,500. Here's 2,000. And then 3,000. So notice how the jump was, see, here's 500. The jump was 500. And then the jump all of a sudden is 1,000. And that's just convention. Every IR plot is like that. That once you get below 2,000, man, it's higher resolution. They zoom in twice as much. Why? Here's a hint. The tables, yeah. Pretty much all that stuff in the tables is in this region down here below 2,000. A majority of that stuff, big time, is below 2,000. So they call that area the what? Oh, so close. Fingerprint. So you've heard this before. Where'd you hear this? Exactly, the fingerprint region. So that's why they changed the resolution there. Melissa, do all vibrations absorb infrared energy? Because they're supposed to be talking about spectroscopy. They're talking about the motion is vibrations, right? And the region of electromagnetic spectrum is heat, or infrared. And so this is the quantized energy, the quantized motions that are doing the absorbing. So a molecule can exhibit all these different types of vibrations. And we'll have pictures of them. Do they all absorb IR? Yeah, because the next question is the real hint, right? So no. So Alyssa, what is an IR active vibration then? One that would, yes, vibrate. They're all going to be vibrating. One that would absorb IR. So they're all not going to absorb infrared. Well, if it's not going to absorb it, what would it probably do? It could scatter it, right? So IR active vibration actually absorbs the IR. So here's some terminology of the different types of vibrations. Okay, and you can't see very well on the screen. Can you see the dots on your? Oh yeah, you can see the dots, right? And on your handout, right? There's dots here. So they're both moving in the same direction at the same time. So a symmetric stretch. Or the atoms are moving opposite direction. Well, not really opposite, right? They're just kind of in sync, but going in different directions, right? At the same time, same distance, different directions. So those would be asymmetric vibrations. And then you've got all these different bending vibrations, right? They're both going down this way, in-plane rocking, in-plane scissoring, right? Out-of-plane wagging. What does that mean? What's this plus and plus mean and minus? Out-of-plane wagging. A hint is kind of the in-plane rocking and in-plane scissoring, how they're just kind of going like this in the same plane. out of plane wagging is probably what? The little minus sign is trying to indicate that atom is going where? Away from you, right? And these two are going towards you all at the same time. So that's why they call it an out-of-plane wagging. Okay, because the plane is the plane of, it's a flat, it's a kind of like a triangle shape, so it's flat. It's got a plane, so but it's going out of that plane. This vibration is, right? The outer atoms are going well out towards you. The center one is going into the plane. So out-of-plane twisting, this one has a plus, this one has a minus. This one there's no sign on, nothing. So there, what's going on? Andrew, what's going on for that one then?
The molecule on the left is coming...
Well, atom. The atom. Atom A and atom B. Atom A is going where?
Away from you, and B is going towards... No. B is going away from you, and A is going
Yeah.
towards you.
Yeah, so that would be my convention too. B is going away from you, C is going towards you. Oh, sorry, B is going away from you, A is going towards you, and C is stationary. Exactly. Okay, so those are the different types of, different types of vibrations. Allowed energies of vibrations. Okay, so I think we... Brandy, can I pull this spring down any distance I want? Can I pull this weight down any distance I want? Well, minus breaking the spring. Right, let's say between here and here. Can I pull it down any distance I want? Yeah, right? There's nothing stopping me. Okay. So when I do that, Melissa, does it change frequency? I gotta do that one or pull it down even farther. Woohoo! Does it change frequency? Right? How? What if I pulled just a little dinky bit? Al, I'm just gonna pull it a little bit. Does it change frequency? Frequency remains the same. It's the amplitude that changes. And you pretty much have to count this to prove it to yourself, right? Like 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. See, it doesn't change. It's only the amplitude that changes. Right? So what's kind of weird, I still think, is I can pull this down any distance I want. Can I do that with a bond? Like for this to increase its amplitude, pretend it's a molecule, it has to absorb what energy? What region of the electromagnetic spectrum for this guy to increase its amplitude? Infrared. Okay. And if it absorbs it, it would be called a what vibration? IR active vibration. So this is an IR active vibration, right? The amplitude increases. But what's weird is it won't, there's only certain amplitude increases it can jump to, right? There's only certain energies. So I can only pull this down certain distances and get it to vibrate if it was an actual bond. It's just totally impossible to pull it down right here and get it to vibrate. It's crazy, right? It's really hard to imagine why, but it is. It's just impossible because the energies are quantized. Right. Okay. So a chemical bond, Andy, is mathematically analogous to a hanging weight. From general physics, the relation between the force to stretch a spring a certain distance is, what was that? F
equals
something X. Yeah, there it is. Kx. So the farther you pull that weight, the more force you need. And K is just kind of like a proportionality constant, right? So the bigger K is, the more force you're going to need to pull it down a given distance. What is different between two bonds, Andy, when one has a larger K value than the other? So they're literally saying, just like, I don't have a picture of it. They're literally saying, here's atom A, here's atom B. Let's make a bond. Well, draw a little spring in there.
Bond is shorter.
Ooh, that's a good difference. The bond is shorter. If it's a larger K, it's going to be a shorter bond. Exactly. Why? Because if it's a shorter bond, that's how I think of things too. If it's a shorter bond versus a longer bond, which one's going to be stiffer and harder to vibrate? The shorter bond, right? Okay, that's a really good idea. Okay, it could be like a double bond in comparison to a single bond, but shorter is still there. Our vibrational energy levels, Andrew, evenly spaced. Now you pretty much have to look at your plot because I don't think you can see it on the screen very well. But see, do these vibrational energy levels look evenly spaced?
No. Or no.
They don't?
I don't think so. I think the top ones look shorter than the bottom ones.
Are they supposed to be evenly spaced?
They're evenly spaced. How come they don't look evenly spaced to you?
Not really. Look at the top ones.
Closer together.
Oh, they do, don't they? I think I screwed it up. But that looks like something that I've copied, doesn't it? Yeah, it says figure 16.3. That's from a book. They're evenly spaced. They're evenly spaced. It's a harmonic oscillator.
You should put not on scale on
Yeah. Yeah, I should. Yes. Each type of vibration, Brandy. So each type of vibration. So here you are. Here's your different types. So you need a more complicated molecule than this, but each type of vibration has its own individual set of blank levels. Energy, yeah, or vibrational. Yeah, there's a lot of words you could have put it in that blank. Quantum levels, right? But the most technical and the best word is vibrational, I guess, energy levels, right? So as you're jumping from one step to the next here, right, absorbs IR energy, goes from one energy level to a next. What's changing here? The amplitude. Does the frequency change? No, it's just the amplitude gets higher and higher and higher and higher until finally the bond breaks. Okay. I think this is also weird. Look at the very bottom. Is that zero energy? Right? What if you're right down here? That's as low as you can go, right? But that means there's still a vibrational energy. Before we couldn't stop the signal. Now we can't stop the vibration. Right? Doesn't matter how cold you get it. There's a 0 point energy. And that's another chem thing. Vibrational energy levels look like an energy ladder. Brandy, how does a vibration travel up this energy ladder? How does it do it again? No. We kind of already answered it. It has to absorb what energy? What type of energy in the electromagnetic spectrum are we talking about? Infrared. It has to absorb infrared to jump up this energy ladder, right? And if it wants to go from here, let's draw a little arrow there. If it wants to go from there to there, it needs to absorb infrared, right? And what changes? The amplitude. What doesn't change? Frequency. And that's awesome because then we can have tables, right? If the frequency changed, we would be screwed and there'd be we wouldn't be building FTIR spectrophotometers. Okay. And what infrared wavelength does it absorb? Well, just remember, This is the delta E. Subtract those two. That's a change in energy. That has to equal the energy of a photon, hc over lambda. hc. I might be getting ahead there, but this is what IR likes to use. They don't like to use wavelength. Remember in UV vis, their x-axis was wavelength. They liked wavelength. And what units did they use all the time, Alyssa? In that UV vis? Nanometers. Right. What do you see very often, Andy, for infrared? You never see nanometers. That x-axis is centimeters to the negative 1. See? It's this frequency with a tilde above it. It's called wave number, or 1 over wavelength. Right? That's 1 over lambda. So it should have units of inverse distance. And they just pick centimeters because it works out the best. Vibrational energy, okay. What do you think, Melissa, is different about the vibration as it travels up the ladder? What changes?
Amplitude.
And what stays the same, Melissa?
Frequency.
Alyssa, frequency, good. Amplitude changes, frequency stays the same. Andy, vibrational energy levels are numbered using a quantum number, V. For a transition to occur, delta V must equal, man, he's getting all the P-Chem questions. Delta V must equal,
I just wrote this in my vocabulary. I don't even remember. I just talked about
good guess. Well, they're numbered from 0, they're numbered integer-wise. So it has to be plus or minus an integer, and it's just going to be 1. I think the only way you can get that is from the reading. This is an example of a selection rule for vibrational transitions. How many different vibrations can a molecule have? Okay. So pretty much it's mathematical determines this. There is a limited number, and there is a number. You draw any molecule, and you can specify how many vibrations that molecule is going to have, simply because it can only move so much. There's only so many possible movements. It depends on the degrees of freedom. 3n is the total number of degrees of freedom. So what does that mean? N is the number of, ooh, there's a good question, atoms in the molecule, right? So n is the number of atoms in the molecule. So, and there's 3n degrees of freedom. Well, why? Because each atom in the molecule requires an x and a y and a z to describe where it's at in space. So if you have n atoms, multiply it by 3, that's a total number of x, y, z stipulations you have to make. Okay? And that's all you specify. That's it. There's no more. You're stuck. That's all you have available to you. So you got to subtract out 3 of these available degrees of freedom because the molecule's flying through space, x, y, z. So you automatically lose 3 because you can't keep it stationary. Translation. And we're not really interested in translation anyway. We're interested in not translational motion, but vibrational, right? FTIR. Okay, and then we're going to lose 3 if it's a nonlinear molecule, or 2 if it's a linear molecule, due to rotation. Because we're not interested in rotation. We're interested in vibration. Okay, so, and how do you know if a molecule is linear or nonlinear? The only way I think you guys know, well, you could Google it, right? But what was in general chemistry? It works most of the time. They called it Vsepar, valence, shell, electron, pair, repulsion theory. Right? We had to draw Lewis dot structures. Right? Anyway, we're not going to be doing that. But the point is that's the easiest way. Google's probably even easier though, right? Okay. So here's the degrees of freedom. 3n minus 6 for linear molecules. 3n minus 5 for, or sorry, 3n minus 5 for linear, 3n minus 6 for nonlinear. Those are the degrees of freedom. That's what's left for vibrations. So if you have water, H2O, is water bent or linear, Andrew? Bent, right? It's got those lone pairs up. See, that's the Vsepar theory. Remember this? If you have 2 lone pairs, you don't put it here and here and make it linear. That's not how it works. Whoop. That's not how it works. That's not, the separate theory says no, it's going to be bent. And if you want, we can review that, but it's bent. It's valence, shell, electron, pair, repulsion theory, separate. Okay, so it's bent. So that means we're going to be following nonlinear, 3n minus 6. So how many vibrations, Brandy, does water have? You have to use the 3n minus 6 formula. Water should have how many vibrations?
So you multiply 3 and then subtract it by 6.
Yep. What's n? N is number of atoms. And water has 3. 3 times 3, 9, minus 6, 3. So we should see 3 here. Okay? So when I click on this little thing, okay, we're going to do this little game here. I'm going to click on each of these, and you can play this game and see how many vibrations it has, but it's going to be kind of given because you're going to see them all. Okay, so that's kind of silly. But I think what's more interesting is we look at each vibration, and you tell me if it's going to absorb IR energy or not. Okay, and there's a trick to doing this, and we'll pick it out. Okay, so there's our 3. Now, in order for a vibration to absorb infrared energy, its dipole moment, I should write this down. This is what's important. An IR, let's just go back up here. You probably should write it right here. Here, IR active vibration. We need to be more specific here. We can't just say it absorbs infrared energy, because now we're going to play the game, hey, does it absorb IR energy? You can tell this by looking at it. You have to have a changing, the vibration has a changing blank. Or the vibration has an oscillating blank. So during this vibration, the vibration has a changing blank, or during this vibration, it has an oscillating blank. What is it? Does anybody know? It needs to be something electrical, because you want this molecule to be interacting with the electric field of the infrared radiation. So it needs to be something electrical. That's your hint. Not much of a hint, but it's a hint, Andy. A changing polarity. If that molecule has a changing polarity, if its vibration is causing it to change its polarity, dang, it's going to interact with an electric field of the right energy, right? It has to be of the right energy in the first place. But if it has a changing polarity, a more technical answer is the next one. It's an IR active vibration if the vibration has an oscillating, starts with a D. Polarity was the first one. Dipole. Exactly. Changing dipole. Okay. Do you remember how you did this whole dipole idea? Right? If you have our bent water molecule, water's an easy one. Okay. You point the arrow in these dipoles where the density of the electrons is higher. Where's the density of electrons highest on this water molecule? Yeah, up here. So you just draw it kind of right through how they draw the dipole. Their convention would be something like this. And then I don't know why, where this comes from. They like to draw a little line down there. I don't know what the point of that is. Right? Maybe make it special. So that's the dipole of water. Now, notice when this stuff starts vibrating, the strength of this dipole is going to be changing. Or the polarity of this thing is changing. Yeah, exactly. And you can see it easier if you see the plot, see the actual vibration. Right? See how that, can't you imagine that, see how the hydrogens are getting closer? This dipole is getting stronger and weaker. It's oscillating at the same frequency as this vibration. And if it absorbs 38, 35 wave numbers, all that's going to change is what again? Amplitude. What's not going to change, Brandy? Yeah, that 38, 35 isn't going to change. It's going to, wave number is always going to change. Okay. And why does it say inverse centimeters again? It's 1 over the wavelength, exactly. In units of centimeters. That's just their convention. Because then they get nice numbers on the plot. You don't have to write 10 to the negative 9 or anything. Okay. So which of these, if any, will absorb infrared radiation?
The first one?
First one will definitely absorb infrared radiation. The second one?
The one on the bottom.
The one on the bottom definitely absorbs infrared radiation.
So yes.
They all do. And it's kind of hard to tell with this one that you're looking at right now. I don't know how to set this up so it keeps going. That, see how, because since this is becoming more linear, right? So it's definitely going to be changing strength. So it's kind of harder to tell. Once you see a totally symmetric vibration, then it'll be a lot easier to tell. This game will get easier. I'm
What
telling
did you
you.
say the clue was?
The clue is essentially just experience here. Well, okay, here's a clue. There's one of these, which is IR inactive, and only one. Two of these vibrations are IR active. One is IR inactive. Which one is the IR inactive vibration? So IR inactive means that it cannot, it doesn't have a changing polarity. It doesn't have an oscillating dipole. The bottom one? Let me pause it. If I pause it, let's see. Okay, here's a good pause. Okay, look at remember these are oxygens? That's carbon. So here's a dipole kind of here, a dipole kind of here. Where's the net dipole? It's probably going to be going this way, right? So this one is definitely going to be changing the whole time that carbon atom's moving. The one up here, man, this guy's jumping up and down. He definitely has an oscillating dipole. The one right here, no matter where I pause it, they're always equidistant, right? No matter where I pause it, they're always equidistant. Look, I pause it here, there. They always cancel out. They always cancel out. And that's what you have to look for if you want to pick out an IR inactive vibration. The IR inactive ones are easier to pick out than the IR active ones, I think. Okay, so that's IR inactive. This one is. Do you see any IR inactive vibrations here? Good. See, you're getting it. That's definitely IR inactive. Are there any other IR inactive?
The very center one?
The very center one. They have to be moving in the same direction all the time. This is moving out. That's moving out. I think they're moving Gosh, it's hard to tell, isn't it? Ah,
I feel like they always cancel each other out.
this one's definitely IR active, right? I think he's right. I think this is IR inactive, right? Because this is moving in the same direction as that guy all the time, equidistant. Yeah, I'd say that's IR inactive. I agree with you. Okay. How about, here's a question. What's this B2G, EN, A2U, A1G? What's this stuff? It's going to be p-chem. Boy, you guys are going to have so much fun when you start talking about symmetry. How about, do you see any IR inactive vibrations here?
The first one.
Yeah, I agree. I think that's the only one. Holy cow. Can you pick out an IR inactive vibration? And all this? Oh man, they're hardly even, you can't even see them move.
Yeah, you can even.
All right, I don't think that's going to be very helpful. You can't really see anything move there. Yeah. See, there's kind of a hint. When you see an A1, that means totally perfect symmetric motion. So look at this guy. This is another one that Andrew picked out, where you had two going, right? Another perfectly symmetric vibration. Yeah, you're going to be going through that again. Yeah, I agree.
Maybe even the one right under it.
Yeah, I agree. Yeah, should move these around somehow. Okay, now you got to cross your eyes. To see the 3D effect. I hate crossing my eyes. You really literally have to cross your eyes and it's going to go 3D. I hate doing it because my mom said they'll stay that way, so I can't let myself do it. If anyone's brave enough to cross their eyes.
I can't, like, look at the screen while.
All right. All right. So how does I think we talked about Fourier transform earlier, right? So I'm not going to go over all that again. But you have your glow bar, or just some hunk of metal or some material that's emitting a lot of heat, and it's going to be a black body emitter because you want it continuous, just like a flashlight is continuous but with light you can see. And then it's going to go into an interferometer. We get an interferogram, go through the sample. So the point is you get something in this time domain, this changing signal, and then we're going to go to the frequency domain and get the frequencies and their intensities that are in this decaying signal. Okay. So you can analyze a lot of stuff with the FTIR. Right? We've done projects on all of these. Microplastics are supposedly becoming a real environmental concern. We've got 2 research posters out there because we've gone down to Corpus Christi and Mustang Island, go to where the sand is beautiful and white, and you just scoop it up anywhere. And they take it back to the lab, and then someone really has to spread through it all, and you find little tiny, this is exaggerated here, but you can find little tiny pieces of plastic. And then we put them on the FTIR to see what type of plastic they were. And there's more of one type than another. And you can plot out the little pieces that you find along the beach and that kind of stuff. But it's supposed to be a real problem because the little fishies are starting to eat this stuff, and it's not good. It's almost becoming a permanent part of the sand. Okay. So that's about it. So have a good weekend.